Imagine trying to teach a dog to fetch by forcing it to watch you play tennis.
Yeah, that is not going to work out too well.
Right. I mean, the physics, the body parts, the fundamental mechanics, none of it aligns natively. And that exact mismatch is basically what robotics engineers face every single day when they try to train a two-fingered robot arm using video of a 21-jointed human hand.
It's a massive headache.
Totally. Welcome to AI Paperslap, where we deliver high-quality, zero-fluff breakdowns of the most important AI and tech research for you technical practitioners. Today, we are doing a deep dive into a paper that actually bridges that gap. It is called Ego2Robot, Scalable Robot Data Synthesis from Egocentric Human Data by Wang and colleagues.
It is a fantastic read.
It really is. So here is your 30 to 60-second summary right up front. This paper essentially solves the robot data bottleneck by building this massive automated pipeline. It converts human egocentric video, like GoPro footage of people doing everyday chores, into synthetic robot training data.
And the scale is just staggering.
Oh, yeah. We are talking about 18,561 hours of data generated across 15 different robot morphologies. And they pull from 4 diverse human ego video sources, which are ANT, EgoDex, VTarray, and Egoverse.
Right. And the core insight for anyone building these systems is the actual mechanics of that conversion. By using mathematically precise action retargeting, depth-aware visual synthesis, and a really rigorous vision language model auditing system, they create synthetic data that fundamentally improves vision language action models.
Or VLA models, yeah.
Exactly. When you mix this synthetic data with real robot data at a 1-to-1 or 3-to-1 ratio, you see these massive out-of-distribution generalizations across visual, embodiment, and semantic shifts.
Which is wild. And this isn't just a clever trick in simulation, right?
No, not at all. It translates to state-of-the-art gains, including a 14% success rate improvement on real-world zero-shot deployment tasks.
So it works on real metal. To understand why this is such a huge leap, we need to step back and look at the fundamental problem in robotics right now, which is the data wall.
Yeah, the data wall is real.
Current VLA models, things like RT2 or OpenVLA, they are incredibly data hungry, and getting that data is just painful. Robot teleoperation is so expensive.
Oh, it is brutal. You need the physical hardware. It is incredibly slow to scale, and human operators get fatigued.
Right. I mean, you get tired after just a few hours of moving a rig around a lab.
Exactly. And even with massive collaborative efforts like OpenX Embodiment or Droid, researchers are totally constrained by the physical limits of a lab environment.
But human egocentric video, on the other hand, is cheap and practically infinite.
Right. People are constantly recording themselves cooking, assembling furniture, picking up objects. That generates a highly diverse, massively scalable data set of interaction.
But the embodiment gap is severe. Like we said earlier, a human hand has 21 degrees of freedom. It has intricate tactile feedback, soft tissue. A standard parallel jaw gripper literally just opens and closes.
It is a totally different form factor.
Which brings us to the core technical hurdle. If you feed a model video of a human hand doing a complex task, how do you translate that to a gripper without just completely confusing the model?
Well, previous attempts at this retarget and render approach, they were usually limited to very small scales or heavily constrained per-task setups. Ego2Robot scales this to over 18,500 hours, like you mentioned, and they do it through a 3-stage pipeline.
Okay, let's break that down. Action alignment, visual alignment, and quality curation, right?
Exactly. Let's start with mapping the hand itself.
Yeah, because if I am looking at a video of my own hand, I have all these articulating joints. How do they mathematically map 21 human key points down to just 2 plastic fingers?
They start by extracting those 21 hand key points using state-of-the-art pose estimation models. Specifically, they use Weiler and DynHamR.
Okay, and those can pull accurate 3D hand poses from completely unannotated video, right?
No manual labeling required.
Yeah.
But the clever part is the mathematical abstraction that happens after that. They create what they call a virtual fingertip.
A virtual fingertip? How does that work?
Well, instead of just mapping the robot gripper to your index finger, which would totally misalign the center of the grasp, they calculate a weighted blend. They take 70% of the index fingertips position and 30% of the middle fingertips position to define this new virtual point in space.
Oh, I can actually visualize that. Like if I hold my hand out like I am going to pinch something, that virtual fingertip is floating right in the empty space between my index and middle fingers.
Yes, exactly. And from there, they define the exact grasp axis.
Okay.
The main grasp axis lies along the jawline, straight from the thumb tip to that new virtual fingertip. Once they have that vector, they calculate the gripper normal axis and the approach axis using cross products.
Which basically ensures a consistent, mathematically stable 3D orientation for the synthetic gripper, right? Regardless of whether the video shows a left or a right hand.
Precisely. It solves the structural mapping completely.
Okay, that makes sense. But I'm stuck on a different physical reality here, and that is velocity. Humans move vastly faster than a standard robot arm safely can.
Oh, absolutely.
If I, chop an onion or toss a block into a bin, my hand is moving at speeds that would make a robotic servo just scream.
Yeah, the gears would not be happy.
Right. So if you map that raw speed into a VLA model, won't the robot try to replicate human velocity and just tear its own gears apart during teleoperation?
That speed mismatch is actually a major reason why raw human video often fails in robot training. But the Ego2Robot pipeline explicitly handles this by subsampling the video frame rates.
So they basically throttle the temporal data to align with safe robot kinematics.
Exactly. For instance, the VTRA dataset features very fast human movements, so the pipeline drops the frame rate down to 25% of its original speed.
Wow, making it 4 times slower.
Right. And Egoverse gets dropped to 45%. By using mathematical subsampling, they align the human action speeds with typical robot teleoperation speeds.
So the model learns a velocity distribution that the physical hardware can actually execute without breaking. That is super smart.
It is. So now you have a slow-motion, mathematically synthesized invisible gripper moving through space. Now comes the visual mapping.
Right, because the model needs to actually see a robot arm doing the work, not a human arm. If I take a frame of GoPro footage and want to replace my arm with a robot's arm, well, first of all, if you remove my arm from the video, you are left with a gaping hole in the image.
You are.
So how do they fix the background?
They use a combination of really powerful foundational vision models. First, they run the segment Anything Model 3 or SAM3 to perfectly segment and mask out the human arm from every single frame.
Okay.
To fill the resulting hole, they use ProPainter, which is a highly advanced video in-painting model. ProPainter looks at the temporal context, like what the background looked like before your arm covered it and what it looks like after.
Oh, and it uses that to seamlessly hallucinate the missing background pixels. Okay, so now we have a clean video of, say, objects on a table with absolutely no human arm in sight. The next step is rendering a 3D robot arm into that space. But wait, a GoPro is attached to a human head. It is bobbing around, it is leaning forward, turning.
It is entirely unanchored, yeah.
So how do you deduce where the heavy physical metal base of a robot should be bolted down in a scene that only exists from a moving, jittery perspective?
Yeah, that is a tricky part. Since the Ego video is unanchored, they have to mathematically deduce the optimal robot base placement using what they call a base pose search.
Okay, how does that work?
They run a grid search in the camera's coordinate frame, testing thousands of virtual mounting points. So they're varying the lateral, forward, backward, and vertical positions, as well as the orientation offsets.
So they are simulating placing the robot base on the table, on the ceiling, slightly to the left, slightly to the right, just over and over. What is the actual success metric they are testing against?
For each candidate position, they check the inverse kinematics, or IK, feasibility. They look at up to 20 spatial extremes, or keyframes, in the hand's trajectory. The algorithm basically asks, from this specific mounting point, can the robot physically reach all the points the human hand reached without breaking its joint limits?
Oh, that is clever.
But they go a step further. They don't just settle for any spot that technically reaches. They optimize the placement so that the robot operates at an average of 65% of its maximum reach.
Ah, I see. Because if you mount the base so far back that the robot has to operate at 99% of its reach, it has no kinematic margin left.
Exactly.
It would be fully stretched out, totally rigid, and just couldn't maneuver around a sudden obstacle.
Right. Operating at 65% ensures it retains a comfortable kinematic margin for complex manipulation. And this search has to be run independently for every single one of the 15 robot morphologies.
Oh, of course. Because a Frankopanda has completely different arm lengths and joint configurations than, say, a UR5E.
Right. So their optimal base placements in the exact same kitchen video will be totally different.
That makes perfect sense for the base. But I have to push back a bit on the final compositing here.
Okay, go for it.
We have our clean background. We know where the robot base is. So we render a 3D Mujiko robot arm and overlay it on the video. How does this not look like a terrible 1990s weather map green screen effect?
Oh, you mean the occlusion problem?
Yeah. If the synthetic robot reaches for a coffee cup or reaches behind a coffee cup, Wouldn't a basic overlay just paint the robot pixels straight over the cup, completely ruining the spatial reality of the image?
A simple alpha overlay would absolutely do that. It would look terrible.
Mm-hmm.
To solve the occlusion problem, they use depth-aware compositing.
Depth-aware compositing.
Yeah. They run a monocular depth estimation model, specifically depth anything V3, over the in-painted background scene.
Okay, so that generates a pixel-by-pixel map of how far away everything in the room is from the camera lens.
Exactly. Then they take the rendered depth buffer of the 3D Ego2Robot, which tells them exactly how far the robot's synthetic pixels are from the camera.
Ah, so it's just a simple mathematical comparison at that point. If the pixel belonging to the physical coffee cup is calculated to be 2 feet from the camera, and the pixel for the robot's gripper is calculated to be 3 feet from the camera, the compositing script knows the gripper is behind the cup.
Right, and it simply hides the robot pixels. It dynamically calculates realistic occlusions on the fly.
Wow.
This seamlessly embeds the robot into the scene. So the VLA model actually learns the correct spatial relationships and depth cues, rather than just learning to look at a robot floating magically over the environment.
Okay, so you have mathematically mapped the action, you've anchored the base, and you've fixed the occlusions. But generating 18,500 hours of this completely automatic, that means you are also automating mistakes, right?
Unfortunately, yes.
Monocular depth estimation glitches, inverse kinematics outputting wild snapping motions. How do you ensure the model isn't just training on complete physical slop?
The pipeline includes a rigorous 3-level quality curation funnel. Level 1 is physics.
Physics, okay.
They run the trajectory through the MuJoCo physics simulator. If there are any IK failures, or if the robot detects a self-collision, like the arm just phasing through its own base, that frame is immediately dropped.
Don't teach the robot to break its own spine. Got it. What is level 2?
Level 2 is statistical. Even with passing physics checks, per-frame pose detections from the unannotated video can be incredibly noisy. So they apply a Savitsky-Golay filter to the trajectory data.
Okay, for the ML engineers listening who might not work with signal processing daily, how does the Savitsky-Golay filter actually smooth the data without ruining the intended movement?
Well, instead of just taking a moving average, which can blur out important sharp movements like a sudden stop when grabbing an object, the Savitsky-Golay filter fits a low-degree polynomial over a sliding window of adjacent data points.
Oh, I see.
This mathematical smoothing preserves the fundamental shape and amplitude of the human's trajectory, but it strips out the high-frequency jitter or per-frame detection noise.
And after that smoothing,
They apply statistical filters to drop entire episodes if they still detect extreme action outliers or sudden discontinuities.
so physics and statistics catch the mechanical errors. But what about semantic errors? What if the math works out perfectly, but the synthetic robot just wildly knocks a bowl off the table instead of placing an apple inside it?
That is where level 3 comes in, which is purely semantic. They use a vision language model, Qwen 3.5, as an automated auditor.
Ah, an AI auditing AI.
Exactly. The VLM watches a 4 frames per second version of the final synthesized video alongside the text instruction for the original human task.
Oh, so it checks if the rendered robot actually achieved the intent of the prompt.
Right.
It's essentially like a strict film director watching the dailies and shouting, "Cut! That is not what was in the script."
This is a perfect analogy.
If the human originally picked up a plate, but the pipeline's artifacts make it look like the robot just slapped the plate across the room, the VLM flags it, and the episode just goes straight in the trash.
This semantic auditing ensures the final dataset is completely pure. If the text says, "open the drawer," the video unambiguously shows a robot opening a drawer.
There is one more crucial data alignment piece here before we get to the real-world results, and that is the action space.
Yes, the camera frame action space.
Because normally, standard robot teleoperation data is strictly calibrated to absolute world coordinates, right?
Usually, yes.
But if I am walking around my kitchen with a GoPro on my head, the world origin is constantly shifting with every step I take. You can't map absolute XYZ coordinates from a moving head. How did they solve that?
They bypass the need for real-world coordinate calibration entirely by converting everything into what they call camera frame relative EF actions.
EEF stands for end effector, which is the gripper.
Right. Instead of trying to calculate where the gripper is relative to the center of the room, all movements are expressed purely as displacements relative to the observer's camera frame.
So the action label becomes, move the gripper 2 inches right of the center of my vision and 1 inch forward, rather than move the gripper to coordinate 10, 20, 30 on the table.
Exactly. This naturally unifies data from totally different camera setups and totally different human heights.
Oh, because it's all relative anyway.
Right. And it also makes the learned policy highly robust to camera perturbations because the model is learning visual motor mapping relative to its own eyes, not an arbitrary fixed point in a lab.
The pipeline is incredibly elegant. But the real question for AI paper slop is always, does this actually train better models? The authors didn't just test this on standard benchmarks, though, right? They evaluated it using RoboTwin 2.0.
Yes, expanding it to 11 independent perturbation axes.
Decoupling the evaluation metrics is a vital contribution here.
Because standard benchmarks often bundle multiple distribution shifts into a single score.
Exactly. If a model fails, you have no idea why. Was the lighting too dim? Was the table a different height? Did it fail because the target object changed? You just don't know. But by explicitly decoupling these into visual appearance, scene layout, embodiment morphology, and task semantics, the authors could pinpoint exactly where Ego2Robot data helps.
Right. And looking at the results, mixing this synthetic Ego2Robot data with standard robot data at a 1-to-1 ratio led to massive out-of-distribution gains.
Visual appearance saw the biggest benefits, right? I saw background robustness went up 4%, lighting robustness increased by 8%, and robot color robustness improved by 6%.
Think about the training distribution here. Why would the model become robust to robot color? Because the pipeline explicitly rendered 15 different robot morphologies.
Right. The model was trained on white pandas, black ARX arms, and silver UR5s. It learned visual invariance to the embodiment itself.
And the background and lighting gains come directly from the insane diversity of human environments. Real kitchens, living rooms, and messy offices that you simply cannot replicate with physical robots in a sterile lab.
Task semantics saw a massive jump as well. Success on unseen object instances, like asking the robot to pick up a type of bottle it has literally never seen before, jumped from 29% to 40%.
That is a huge leap for zero-shot generalization.
And they also evaluated on eBench, which uses a high-mounted camera very similar to a human perspective. On eBench, the 3-to-1 mix, so 3 parts synthetic data to 1 part real data, achieved a 12.1% gain.
Yeah, when you align the viewpoint bias of your synthetic data with your target deployment setup, the benefits of co-training are amplified tremendously.
But I'm looking at the cross-embodiment results, and I really want to challenge the universal applicability of this. Pre-training on the 15 synthetic robots clearly helped most models. When tested zero-shot on the ARX X5, success improved to 51%.
Which is fantastic.
Right, and the UR5 WSG improved to 31%. But the Frankopanna model completely bombed. It stayed under 7% success. If this camera frame relative data is so mathematically generalized, why did the Franka fail so hard?
Well, that highlights the absolute limit of zero-shot transfer, which is the kinematic gap.
Oh, okay.
Like for Frankopanna has a 7-degree of freedom arm with a very specific joint structure, reach limit, and kinematic chain. Its physical realities are simply too far removed from the dominant training embodiments in the dataset.
So the camera frame action space is a powerful mathematical abstraction, but it cannot override fundamental physics.
Exactly. If the target robot has to twist its joints in a fundamentally different way to achieve the same end effector position, it will fail without fine-tuning. Ego2Robot vastly expands generalization, but physics wins in the end. You still need some level of embodiment alignment for complex zero-shot transfer.
That is a really crucial caveat for you ML engineers listening to keep in mind. So the simulation benchmarks prove the concept, but the ultimate test is physical deployment. Let's talk about real metal.
Yeah, and before they deployed to the real robot, they ran a fascinating ablation study on scaling. As they scaled the pipeline from rendering one morphology to 5 to 10 to 15, the model's performance steadily improved.
Makes sense. More diversity, better performance.
Right. But the most surprising finding happened when they took the raw, unrendered egocentric video, just the standard human hand doing the task, and threw that back into the training mix alongside the synthetic robot data.
Wait, you mean just feeding the VLA model raw GoPro footage of a fleshy human hand, unedited?
Yes.
That's wild.
When they combined the 15 morphology rendered data with the raw human video, performance jumped again, peaking at 37.3%. The raw human data essentially acted as a 16th morphology.
That is so funny. The model just views a human hand as a really weird, fleshy end effector.
It does. It introduces slightly different visual appearance and action distribution, which forced the model to learn even deeper robustness.
So how did it perform on the real robot? They tested on an ARX Acone platform, doing 5 long horizon tasks, right? Things like put blocks into a drawer, fold a towel, sweep trash, and insert a screw.
Yes. And they tested a specific workflow that completely changes the economics of robot training. They recorded just about 7 minutes per scene of casual, egocentric play video.
So a human just wore a camera and did the tasks naturally.
Right. They ran that 7 minutes of video through the Ego2Robot pipeline to convert it to the Ego2Robot's morphology, and then mixed it with a tiny data set of just 20 standard teleoperated demonstrations.
And that configuration, the mix plus Ego2R play, achieved a 14% gain on the put blocks task over the baseline model trained only on robot data.
It's incredible.
To be clear about the implications here, as an ML engineer, if I need my factory robot to learn a new insertion task tomorrow, I could theoretically strap a camera to my head, do the task myself for 10 minutes, run it through Ego2Robot, and significantly boost my robot's zero-shot success rate without spending hours teleoperating the machine. That feels like a workflow cheat code.
It absolutely democratizes data collection.
Yeah.
You are no longer gated by how many hours your technicians can spend carefully teleoperating a specific robot arm with a VR controller.
Right.
You can leverage the vast supply of human video already on the internet, or casually collect your own in minutes and just let the math do the heavy lifting of action alignment, base pose searching, and visual retargeting.
Let's summarize the immense value here for practitioners. Ego2Robot effectively unlocks the internet's vast supply of human video for scalable robot learning. It solves the embodiment gap with incredibly clever math.
Yeah, using IK grid searches to find the optimal kinematic base pose.
Right, and depth-aware compositing against MuJoCo buffers to fix occlusions, and Qwen 3.5 VLM auditing to ensure semantic purity. For anyone building data pipelines for physical AI, this approach is basically a paradigm shift.
It proves that the true bottleneck in robotics isn't necessarily the lack of data, but our ability to translate existing, abundant human interaction data into a mathematical format that a physical robot can actually parse and execute safely.
But I do want to leave you with a forward-looking thought, drawn explicitly from the limitations of this current paper. Right now, this retargeting pipeline mathematically forces a highly articulated 21-jointed human hand down to a simple 2-fingered parallel jaw gripper.
Right, it discards all that beautiful, fine-grained finger articulation.
But what happens when we combine this pipeline with the next generation of dexterous, multi-fingered humanoid hands? And as video generative models continue to improve rapidly, will the minor visual artifacts from in-painting disappear completely, creating synthetic video indistinguishable from reality? The era of truly universal, infinitely scalable robot training data might just be a few human videos away. Think about that next time you are building your data pipeline.